Hi, welcome to the Olympiad Geometry Club. Let's continue our study. Today we're going to talk about an extremely difficult problem. It's probably the most difficult problem I've ever seen. So this is from IMO 2011, the sixth one. Let's just check on that. Let triangle ABC be an acute triangle, as I show the figure here. Triangle ABC, it's an acute triangle with a circumcircle K. This is a circumcircle. Let L be a tangent line to K. So here I just choose a point D and I draw the tangent line XYZ. Right, that's a tangent line, which is line L. And let L1, L2, L3 be the lines obtained by reflecting L in the sides BC, CA, AB. So line L reflecting to BC, we get L1. Right? It doesn't matter the name, it's useless. Here, this is L1 and this line reflecting to CA, we get L2. And this line reflecting to AB, we get L3. So this is L3. And we want to show that the circumcircle of the triangle determined by the lines L1, L2, L3 is tangent to the circle K. So what is the triangle determined by L1, L2, L3? Look at L3 and L1 intersect on point F. And L3 and L2 intersect on point E. L1 and L2 intersect on point G. So basically, the triangle EFG is a triangle that formed by these three reflecting lines. And we want to prove that the circumcircle of the triangle EFG is tangent to the circumcircle of triangle ABC. Okay, so for this problem, the first impression of it is that we can just do a false brutal calculation, right? And to keep the problem to be easy enough, we can do something like this. Let me just draw here. So let me just introduce this method first. We can think of that we have a triangle with a circumcircle which centered on the original point, right? So this is 0, 0. And we can just force the tangent line to be this one, right? -1, 0. That's easier for us to do the calculation. And now we have to arbitrarily choose a triangle which can be A, B, C, which is XA, YA, XB, YB, XC, YC here, right? And now what we have to do is that we just calculate for the line equation of this one reflecting to AB here and reflecting to AC. So roughly say here, and reflecting to BC, roughly say it's the same, right? So we calculate for these, it may not be the same, it's just another angle. So we calculate for the line equation and we find the intersection point. And based on the intersection point, we can find assume that we already find the intersection point. Basically, we have the coordinate of these three, the triangle EFG, right? we know the coordinate of the triangle EFG. And now it's easy to find the circumcenter based on the perpendicular bisector lines, right? We have to write down the line equation for this line, for like this line, and then we find the circumcenter, and then we find that the distance from the circumcenter to this to the original point, right? It equals to, so let's see, D O E F G minus minus 0, 0, right? It equals to R O E F G minus, because we assume that this is a circle with radius as 1, so minus 1, right? We just need to prove that. We have to calculate a lot, right? And it's kind of like a way that you want to do as an exercise, but you don't want to do it when you are on the exam, especially this computation, right? Too much calculation. So back to our pure geometry solution here. The first thing we want to do is that just look at the figure and think about that. We want to find that the circumcircle of triangle ABC is tangent to the circumcircle of triangle EFG, right? Which means it would be easier if we can find the tangent point first, right? So here I gave the when I see this problem, I want to break this problem. I know this is a very difficult problem, so I have to break this problem to be several steps, right? So following the several steps, basically I turn the hard problem into several different problems, but maybe a little easier than this problem. So we break each one and then we can put them together to solve the whole problem. So the idea is that first, find the possible tangent point, right? So we need to find the possible tangent point and find the property of this tangent point. We need to find because in all of these circles are tangent on a weird point. This weird point is not just a tangent point, it has some other properties. So we need to find some other properties first and try to prove that. So try to think this as a possible tangent point, and then the second part, we want to prove this point is on the circle ABC and also on circle EFG, right? Basically, we just prove, we find a possible tangent point, and if we can prove that this point is on the circle ABC and on the circle EFG, at least it's an intersection point for the two circles, right? And then the third part is that we just need to prove this point is so think about that. We have two circles here, right? We have two circles. We want to prove that this is we know this point is on the smaller circle and the larger circle at the same time. So we want to prove that this point is a tangent point, right? Prove that this point is a tangent point of the two circles. So that's the three steps. we need to find the possible point first. To find that, let's just look at the figure. Think about this figure. What we have from the problem set is that we arbitrarily find a point D on the circumcircle of triangle ABC, and then we draw the tangent line, and then we do the reflecting lines, and then we form another circle, right? So if we slow down, just think about that, we find a point on the circumcircle of triangle ABC, and we do reflecting points, right? We find the tangent line, we do reflecting lines, so we can still do the reflecting points, right? From this point D, we find the dA prime, right, which is reflecting of the side BC, and we find the dB prime, which is a reflecting point from D to the side AC, and also we find DC prime, which is a reflecting point from D to the side AB. This just remind us the Simpson line, right? So if you look at the figure, basically DDA prime is perpendicular to BC, DDC prime is perpendicular to AB, and DDB prime is perpendicular to AC. And we know these 3 points as a midpoint of DDA prime, DDC prime, DDB prime. And these 3 points form the Simpson line, right? And since they are the midpoint of each side, which means these 3 points, the DB prime, DC prime, and DA prime, these 3 points, are collinear. And based on this, we know that, let me write down let me just write down here. Based on this, we know that dB equals to DC prime, right? Because D and DC prime are symmetrical points of set AB. So dB equals to DC prime B DC prime, right? B to the DC prime. And dB also equals to B to the DA prime. Now we just look at here. We find an isosceles triangle. Triangle BDC prime DA prime is an isosceles triangle, right? This is an isosceles triangle. And similarly, because DA equals to ADB prime equals to ADC prime. So we know that triangle ADB prime DC prime is an isosceles triangle. And for the DC, we know that DC equals to CDB prime, right? DC equals to CDB prime, and also equals to CDA prime, right? Sorry, here I draw it wrongly. This should be connected to DA, not F. Okay, yeah. So we know that CD equals to CDA prime. So we know that triangle CDA prime DB prime is an isosceles triangle. Okay, we get 3 isosceles triangles now. Now let's think about what else we can get from this. We want to calculate for the angle D, for example, in the triangle DC prime BDA. So let's calculate the angle DC prime BDA prime. Okay, we want to calculate for this angle. Let me move this a little bit here. Okay, let's try to calculate the angle DC prime BDA prime. It equals to twice of angle DBC. Let me write down it like this. It equals to angle DBDA prime minus angle DBDC prime, right? The angle DC prime BDA prime equals to angle DBDA prime minus angle DBDC prime, which equals to twice of angle DBC, right? Because angle DBDA prime is twice of angle DBC, minus twice of angle DBA, right? Because angle DBDC prime, that's twice of angle DBA. So it equals to twice of angle DBC minus angle DBA, which is twice angle DBC minus angle DBA, which is angle ABC. So it equals to twice of angle ABC. Right. So now we know that the angle DC prime BDA prime is twice of angle ABC. So this angle is twice of angle ABC. Now let's look at the angle DC prime ADB prime. Okay, the angle DC prime ADB prime. This angle. It equals to 360 minus angle DADC prime minus angle DADB prime, right? It equals to 360 minus this angle minus this angle. That's the angle DC prime ADB prime. So it equals to 360 minus twice of angle. So this one, the angle DADC prime, that's twice of angle DAB. And minus the angle DADB prime is twice of angle DAY, right? So this one, it equals to the angle DAY. The angle DAY equals to angle DBA, right? The angle DAY, this angle, sorry, equals to angle DBC, right? This angle equals to angle DBC. Right. So it equals to this one, 360 minus twice of angle DAB, which is angle DCB, right? Twice of angle DCB minus twice of angle DAY is angle DBC equals to 360 minus twice of angle DCB minus twice of angle, the angle DBC can be break as angle DBA plus angle ABC, which is angle DCA plus angle ABC, right? So twice of angle, so the angle DBC is DBA plus ABC, so DBA equals to DCA, so twice of angle DCA plus twice of angle ABC. Okay, and it equals to 360 minus twice of angle DCB plus angle DCA plus angle ABC, right? DCB plus angle DCA, which is angle BCA, right? DCB plus DCA, which is angle ACB. And angle ABC here. So it equals to twice of 180 degree minus angle ACB minus angle ABC equals to twice of angle BAC. Right, so we got that angle the angle DC prime A dB prime. This angle equals to twice of angle BAC. So it's similar to here, right? The angle DC prime B DA prime equals to twice of angle ABC. So now let's look at the angle DB prime C DA prime. Okay. Let me actually do this. Yeah, that's better. Okay, now let's look at the angle DB prime C DA prime. DB prime C DA prime, right? We want to calculate this angle. And this angle equals to twice of angle DC DB prime plus twice of angle DC DA prime. DC DA prime equals to twice of angle DC. No, there's no twice, right? So, sorry, the angle DB prime C DA prime equals to angle DC DB prime plus angle DC DA prime, right? And it equals to twice of angle, so DC DB prime, that's twice of angle DCA plus twice of angle DC DA prime, that's twice of angle DCB. So it equals to twice of angle DCA plus angle DCB, which equals to angle ACB, right? So basically, we find that the triangle DC prime B DA prime is an isosceles triangle, and the angle DC prime B DA prime is twice of angle ABC. And the triangle ADC prime DB prime is an isosceles triangle, and the angle DB prime ADC prime is twice of angle BAC. And the triangle DB prime C DA prime is an isosceles triangle, and the angle DB prime C DA prime is twice of angle ACB. That's what we found so far. Okay, now let's think about how can we find the possible tangent point. So if you look at this figure, if I extend BC, right? We extend BC and meets this tangent line on the point X. Similar here, we extend it to meet the tangent line on the Y. So we do this and we find this X point. And we already know that angle DC prime BDA prime is twice of angle ABC. Maybe this one is still easier to look at. So let's just extend BC here. So because BA, if we extend it, we know that what is point Z? Point Z is the intersection point of line L and line L3. And it must be the concurrent point of line AB, right? Because line L3 and line L are symmetrical to line AB. So these three lines are concurrent on point Z, which means the angle ABC, right? The angle ABC equals to angle BXZ plus angle BZX, right? Angle ABC equals to this angle plus, so it's not necessarily passing through this point, right? So like this, plus this angle. Again, angle ABC equals to this one plus this one, right? And we know that the angle YZ DC prime or XZF, right? Angle XZF equals to twice of angle BZX, right? This angle is twice of angle BZX. And also angle DXF is twice of angle DXB, right? DXF is twice of angle DXB, which means the angle ZFDA prime equals to twice of angle DXB plus twice of angle, it equals to this one plus this one, so twice of angle DXB plus twice of angle XZB, right? And we know this one plus this one, that's the angle ABC, so meaning it equals to twice of angle ABC. And we already know that angle DC prime BDA prime equals to twice of angle ABC. So we know that angle DC prime, so ZFDA prime, that's a DC prime FDA prime, right? So angle DC prime FDA prime equals to angle DC prime BDA prime equals to twice of angle ABC. And this tells us that DC prime B F DA prime are cyclic, right? DC prime B F DA prime are cyclic because this angle equals to this angle. Okay, so we have the conclusion that DC prime B F DA prime are cyclic. these 4 points are cyclic. And similarly, we can directly prove that DC prime A, DB prime E are cyclic. Okay, it's just the same way to do that, right? We find this angle equals to twice of summation, and then we can directly prove that DC prime A, DB prime E are cyclic. Also, DB prime C, DA prime G are cyclic. Okay, you just use this exactly same method, we can prove this. So now we find that DC prime, DA prime, F, B are cyclic, and DC prime A, DB prime E are cyclic. Also, DB prime C, DA prime G are cyclic. Because these 4 points are cyclic, I can draw the circumcircle for the triangle or for the quadrilateral DC prime B, F, D prime. Right, I can draw that circumcircle, and we know that B is on the circle K, and B is on this circle, so we can say that there must be another intersection point for the circumcircle of the triangle DC prime BDA prime and the circumcircle of the triangle ABC. Right, let's call this point as P. So this is a possible tangent point. You may ask why I know that. I draw this figure very, very carefully, and I feel so. It just happens to be very close to each other. I mean, I use a compass and a ruler to draw the figure. I didn't draw it on the computer. So I just want to mimic the situation in the exam, right? And I find that those are very, very close. I feel that that might be the same point, and then that's the whole idea. So basically, for this very, very difficult problem, you have to draw a very, very accurate figure. It helps a lot. So anyway, we find this intersection point now, right? And I want to prove that this point is not only on the circumcircle of the cyclic quadrilateral DC prime B FDA prime, but this point, now this is the intersection point of this circle and this circle, right? But I would say this is also on the circumcircle of quadrilateral E DB prime A DC prime, and it's also on the circumcircle of quadrilateral DB prime C DA prime G. Okay, let's prove that. Now, think about how can we prove a point is on another circumcircle. We just need to prove, for example, if I want to prove that point P is on DB prime C DA prime G, I just need to prove that DB prime C P DA prime, these 4 points are cyclic, right? I just need to prove that, which means I just need to find it. Means that I want to prove P is on circumcircle of circle DB prime CDA prime, right? We want to prove this, which means we want to prove DB prime CPDA prime is a cyclic quadrilateral, right? Which means we just need to prove that angle DA prime PC plus angle dA prime dB prime C equals to 180. Right, we just need to prove this. Okay, now think about how to prove that. The first thing is that we want to find the angle dA prime dB prime C, right? We want to find this angle. So, and we want to find this angle. So, the angle dA prime dB prime C, this angle, just because triangle dB prime CD prime is an isosceles triangle, so we know that the angle dB prime C dA prime, right? Angle dB prime C dA prime. We just find the angle of that. It equals to twice of angle ACB, right? So the angle dA prime dB prime C equals to 180 degree minus twice of angle ACB and divided by 2, which equals to 90 degree minus angle ACB. That is angle dA prime dB prime C. And what about the angle dA prime PC? Angle dA prime PC equals to angle dA prime PB plus angle BPC, right? And the angle dA prime PC, because DC prime B, F, dA prime P are cyclic, so the angle dA prime PB equals to angle dA prime DC prime B, right? So it equals to angle dA prime DC prime B plus angle BPC, because ABPC are cyclic, so angle BPC equals to 180 degree minus angle BAC. So 180 degree minus angle BAC. And it equals to, see, we want to calculate the angle dA prime DC prime B, right? The angle dA prime DC prime B, which equals to 180 degree minus, because triangle DC prime A dA prime is an isosceles triangle, and we know that angle DC prime B dA prime is twice of angle ABC. So the angle dA prime DC prime B can be calculated as 180 degree minus twice of angle ABC divided by 2, right? That's the angle dA prime DC prime B, right? And we still plus 180 degree minus angle BAC. So that is the angle dA prime PC, which equals to 90 degree minus angle ABC plus 180 degree minus angle BAC. So it equals to 270 minus angle ABC minus angle BAC. Oh, let me write it here. Right? Now let's look at this angle plus, so the angle dA prime PC plus angle dA prime dB prime C, right? We want to prove that the angle dA prime PC plus angle dA prime dB prime C equals to 180 degree. So let's add them together, which equals to 90 degree minus angle ACB plus 270 minus angle ABC minus angle BAC, right? It's equal to 360 minus these three, right? Angle ACB, ABC, and BAC, that's 180 degree. So it equals to 180 degree, which means dB prime, CP, dA prime are cyclic, which means P is also on the circumcircle of the quadrilateral dB prime C, dA prime G, right? So P is a common point for this circle, the circle K, and this circle, right? which I draw it here. Right. And also we want to prove that P is on the circumcircle of the quadrilateral E dB prime A DC prime, which we can use a similar way. We can calculate for, we can just say that A dB prime DC prime, right? We want to calculate for the angle DC prime P dB prime. DC prime P dB prime. We just need to prove that dB prime A DC prime P is a cyclic quadrilateral, which means we just need to prove that the angle DC prime P dB prime plus angle DC prime A dB prime equals to 180 degrees, right? So let's try to do that. It equals to the angle DC prime A dB prime, that's twice of, this is twice of angle BAC, right? So now let's calculate for this one, DC prime P dB prime. DC prime P dB prime. It equals to so this angle equals to this one equals to angle BPC minus angle BPDC prime minus angle DB prime PC, right? The angle DC prime P dB prime equals to angle BPC minus angle BPDC prime minus angle DB prime PC, right? So think about that. We already proved that dB prime CP dA prime are cyclic, right? So the angle dB prime PC equals to angle dB prime dA prime C. So it equals to angle BPC minus angle B, and angle BPDC prime equals to angle BDA prime DC prime. So angle BDA prime DC prime minus angle DB prime DA prime C, right? Because DB prime CP DA prime are cyclic. So this angle equals to this angle. And we know how to calculate for that angle. So it equals to, let me rewrite it here. So it equals to the angle BPC, which is 180 degree, minus angle BAC, minus the angle BDA prime DC prime, that's half of 180 minus twice of angle ABC. And angle DB prime DA prime, DB prime DA prime C, that's half of 180 minus angle twice of angle ACB, right? So this is 180, this is minus 90, that's 0. And for here, it's minus angle BAC. For here, we have positive, right? So it's twice of angle ABC plus twice of angle ACB minus angle BAC. Right. And remember, we want to calculate for the angle DC prime P Oh wait, this is just 1, right? There's a half in front, so just 1. And we want to calculate for the summation of the angle DC prime PDB prime plus the angle DC prime ADB prime, which is twice of angle BAC. So we add it here, plus twice of angle BAC. The total would be 180 degree, right? Which means P is also on the circumcircle of the quadrilateral E dB prime A DC prime. Okay, so for now, we just proved several things. First, we find a point P, right? That's, as we call it, a possible tangent P. And we also proved that this point P is on the circumcircle of the triangle DC prime B DA prime, also on the circumcircle of the triangle DB prime A DC prime, and also on the circumcircle of triangle on the circumcircle of the triangle DB prime C DA prime, right? I didn't draw it out, so like this. Now, if we go back to our first step, we just find this one. And we already know this point is on the ABC, the circumcircle of ABC, triangle ABC, right? Just because when we start, we say that this P is intersection point of this circle to the circumcircle of the triangle ABC. So it's already on the circumcircle of the triangle ABC. So we want to prove that this point P is still on the circumcircle of triangle EFG, on the circle EFG, right? Circle EFG. So how can we do that? We want to prove that P is also on the circumcircle of the triangle EFG. You can see I draw it out here. We want to prove that P is on this circle as well, which means we want to prove EGFP are cyclic, right? And if you look at the angle DA prime FP, this angle, the angle DA prime FP, D prime FP, it equals to the angle D prime DC prime P. Right? Because they are all on this circumcircle, so the angle D prime FP equals to angle D prime DC prime P equals to this one. And because we just proved that E dB prime A DC prime P are cyclic, so let's say the E dB prime DC prime P, this quadrilateral is a cyclic quadrilateral, right? So the angle DA prime DC prime P, this one, equals to angle DB prime EP. Right? So this one equals to this angle. And because see, E dB prime DC prime P are cyclic, so this angle equals to this angle, which is angle GEP. Right? Now we find that angle DA prime FP equals to angle GEP, which means EGFP are cyclic, which means P is on the circle EFG. right? So now we just prove that P is a common point, or P is at least the intersection point of the circle ABC and circle EFG. So now let's think about how to prove that P is a tangent point. We proved that P is on the circumcircle of triangle ABC, and we proved that P is on the circumcircle of triangle EGF. So I didn't draw this line here, but you can see the quadrilateral here. Okay. Now just think about that. We draw a tangent line through P to the circle EFG, right? So if we want to prove that the circle K is tangent to the circle EFG, we just need to prove this tangent line is not only the tangent line of circle EFG, but also it's a tangent line of the circle ABC, right? And then we connect GP. So we know that the angle, you see this is a tangent line, right? I call it PI, right? It meets GDA prime on the point I. So this is a tangent line, and this is a chord, right? So the angle IPG, the angle IPG equals to the circular angle reference to this chord GP. So it equals to angle GEP, right? This angle equals to the angle GEP. And so it equals to the angle GEP here. And we want to say that the GP meets a circle ABC on a point H, right? So if IP is a tangent line of the circle ABC as well, then it must exist that angle IPH, which is angle IPG, equals to angle HCP, right? Equals to angle HCP, which means we just need to prove that angle GEP equals to angle HCP. We want to prove that this angle equals to this angle, right? Then we proved that the PI is also the tangent line of the circle ABC. But if you look at this angle and angle HCP here, they are far away, right? So look at here, the angle GEP, we just used it, right? We just use it to prove that P is on the circumcircle of triangle EFG, which means the angle GEP equals to angle GEP equals to angle DA prime FP. Right? The angle GEP, because GFPE, we just prove that this angle DA prime FP equals to angle GEP, right? Which means now we want to prove that this angle equals to this angle, right? The angle DA prime FP. And we know that angle DA prime FP equals to angle DA prime BP. Right, because F BF dA prime P are cyclic. So the angle dA prime FP equals to angle dA prime BP. And if you look at here, we want to prove that angle it equals to angle HCP. And we know that angle HCP equals to angle HBP. Which means we want to prove that angle dA prime BP equals to HBP. Which means we just want to prove BHDA prime are collinear. Right? We want to prove that these 3 points are collinear. Or we can transfer the demonstration, or we can transfer the claim as the following one. If we simply connect the dA prime B and PG, if we simply connect the dA prime B and PG, the intersection point is H. We just need to prove that H is on the circumcircle of triangle ABC, then we're done, right? So now the problem is that how to prove the intersection point of GP and BDA prime H is on the circle ABC. Now we want to prove this one. So if we want to prove that this H is on the circumcircle of the triangle ABC, basically we just need to prove that HBCP are cyclic, right? HBCP are cyclic. We just need to prove that. Which means we want to prove that angle PHB plus angle BCP equals to 180 degrees. That's what we want to prove. And we know that angle PHB equals to angle dA prime HG, right? So it equals to prove that angle dA prime HG plus angle BCP equals to 180 degrees, which is equivalent to, because angle dA prime HG plus in the triangle GHDA prime, right? This angle plus these two angle equals to 180 degrees, which means we just need to prove that angle HGDA prime plus angle HDA prime G equals to angle BCP, right? We want to prove that angle HGDA prime plus angle HDA prime G equals to angle BCP. So because CP dA prime dB prime G are cyclic, which means angle dA prime GH, which is angle dA prime GP, right? This angle equals to the angle dA prime CP equals to this one. So here the angle HG dA prime equals to angle dA prime CP. So if we move this one to the right side, we know that angle BCP minus angle dA prime, this is equivalent to prove that angle HDA prime G equals to angle BCP minus dA prime CP. BCP minus angle dA prime CP, which is angle BC dA prime. right? We want to prove that angle HDA prime F equals to angle BCDA prime. Now think about the angle BCDA prime. Angle BCD prime equals to angle BCD, right? We want to prove this one. And angle BCDA prime equals to angle BCD, because D and DA prime are symmetrical pointed to BC, right? So angle BCD prime equals to angle BCD, which equals to angle BAD, right? Equals to this angle, right? So the angle BCD equals to angle BAD, because they are on this circle K. And because this is a tangent line L, so we know that the angle DAB equals to angle XDB, right? It equals to angle XDB. And because D and DA prime are symmetrical to the BCX, this line, so the angle XDB equals to angle XDA prime B. Which is angle HDA prime G, right? Right? Angle XD prime B, that is angle HD prime G. Okay, now we just prove that if we connect GP and BDA prime, the intersection point is H, and this H is on the circumcircle of triangle ABC, right? So that is saying this tangent line reference to the circle IPG, which equals to angle PFDA prime, right? Equals to this angle, and we just proved that this one equals to the angle DA prime BP, right? And due to H is on the circumcircle of the triangle ABC, so it equals to angle HBP, which equals to angle HCP, which means that PI is a common tangent line for the circumcircle of the triangle ABC and the triangle EFG. Okay, so that's about this problem. It's really a difficult one. I don't know. To be honest, I don't think I can solve this problem if I'm in the competition, because it's definitely take me more than 3 hours to figure it out. So just a short review what we did here, what we can learn from this problem. The first thing I think is most important, that we can figure out a solution, and we know that it's not a very good solution. We can force Bruto to calculate it, but I don't recommend this way. And then we think about how to do it in a pure geometry method. The first thing is that we want to find the possible tangent point, and then we want to prove that this point is both on the triangle, on the circumcircle of the triangle ABC, and on the circumcircle of the triangle EFG, right? And then we want to find a way to prove that this point is not an intersection point, but a tangent point. So based on that, what we start is to just do a little research on this figure itself, right? We do a little research on the figure to find the isosceles triangles And when we find the isosceles triangles, we find that we calculate for this angle, and it gives us an idea, right? Because it's twice of angle ABC, it's quite weird, right? So we want to find if there's any other angle equals to the twice of angle ABC, which is a reasonable thought just because we have so many symmetrical lines, which we should be able to find some twice angle relations. And based on that, we can confirm that DC prime, P, F, D prime, these 4 points are cyclic. And then the guess would be that this tangent point, when I draw the circumcircle of this one, I just find it's so close. Then the idea is that this intersection point would be the possible tangent point. And then we want to prove that this point is also the concurrent point of other circumcircles. And based on that, we proved. And then we go back to here, we want to eventually prove that this is a tangent line. Right? How to prove a tangent line? Several methods. We can try to figure out that the circumcenter of the triangle ABC and the circumcenter of the triangle EFG, right? We prove that these 3 points are collinear, which is very, very difficult in this method, in this geometry, right? We don't know how to find that relations. Then another idea is that if it's a common tangent point, right, that means if we draw a tangent line for one circle, it must be the tangent line for another circle. Then we can use the angles to do the proof. Okay, so that's this problem. I hope you like this video. If you think this is helpful, please click the like button, comment, share, and subscribe to the channel. If you think I work so hard, please share it to someone would be think this would be useful. Thank you very much. See you in next one.